when we collect data, we want people to know how closely we came to actually representing the population and the data we said that we were showing in our analysis. So one way to communicate that is by calculating a margin of error. A margin of error for a sample population is a measure of the confidence interval for the statistic. And a confidence interval just means that I calculated this value, but I think that it really could fall in between this number and this number. And the more data we collect, we can actually get closer to that actual value. It's called the law of large numbers. So the more times that you run the statistics on a larger number of people, we get closer to our actual sample statistic that we're trying to calculate for. So the first thing that you have to do is calculate a critical value. So one example of a critical value is the mean. So finding the average or the measure of center by adding up all of the numbers and then dividing by the number of data points. So we have 10 healthy people here, and we've taken the temperature, and we're going to find the mean body temperature. So the sum is going to be 987.84 when we add all of these numbers together. You can pause the video and check my math if you would like. And then we divide by 10, which means for this group, they have an average body temperature of 98.784 degrees Fahrenheit. And you know that we believe that the actual average body temperature is about 98.6. So this group is actually a fairly good representation of a larger population. Another way to show and calculate data is from a dot plot. So for this dot plot, we have all of these dots. There's 100 dots that represent groups of 10 people. And so they tell us that the mean for this group is 98.6. And they want us to calculate a reasonable margin of error for this population. So basically, how closely does this group represent the global population for body temperature? So to calculate from a dot plot, we use the range. And remember that the range is your maximum value minus your minimum value. So the largest point we see here is 99.12. The smallest value on the left is 97.94. And we would take and subtract those two numbers. And we get a range of 1.72. Now, one thing to notice also is that most of our data is probably in this region just by looking. So most of the data is clustered right around that 98.6. We have a few things that lie outside of those values. And that's kind of what we're wanting to show people with that margin of error. So we're going to take that range and divide it by 2. And that is going to be our margin of error because we're estimating it for this dot plot. If we were asked to give the range of values for that margin of error, we would take 98.6 and we would add the 0.86 and we would subtract the 0.86. And so we're saying that basically we found a mean of 98.6, but we think that a certain amount of time that we were to do this experiment or observation or whatever type of study we're doing, we think our mean would actually fall in between these two numbers. So the graph below is the same type of study, sample mean body temperature, but now we have groups of 20 rather than groups of 100. So we've doubled the population from our last graph. And so one thing that you want to notice is that as we are increasing our population, that our range is getting smaller, right? So if we're calculating reasonable margin of error for this group, we would take the highest value that we see on this graph, which is 98.98, and we would subtract 98.24, and we would have a range of 0.74, so a lot smaller than the previous graph. Divide by 2, so our margin of error is going to be about 0.37 from the mean. So our previous graph was 0.6 margin of error. This is about half of what we had previously, when we had a group of 1,000 people, and now we have a group of 2,000. What this tells us about this data collection process is that as our sample size increases, so as we collect more data, then our margin of error is going to get smaller and smaller and smaller, because as I go out and get more of the data from the actual population, then my sample is a better representation of that data, which means there's not going to be as much error in my critical value. For this course, you're going to be given your formula for your confidence interval. The one that we use most often is going to be for a 95% confidence interval. Now, there are a couple of ways that you will hear people interpret confidence intervals. Some people say, I'm 95% confident that my mean is in between this number and this number. Now, I don't know how to be 95% confident. I'm either confident or I'm not. And so when I took statistics and was learning, my professor explained it that I'm 100% confident that 95% of the time, the actual critical value will fall in this range of numbers. So if I were to perform this particular study multiple times, 95% of the time, the value or the mean would fall in between these two numbers based on the statistics and the data that I've already collected. So for a 95% confidence interval, we use the constant 2, and again, that number changes because you can change your confidence intervals. In this course, we're only going to focus on a 95% confidence interval, and we're not going to calculate the number 2. We're just going to know that it's part of our formula, multiplied by our standard deviation, which again will be given to you. We don't have to calculate it at this level. And then divide by the square root of n. So again, S of x is your standard deviation. So how far away from the mean your data falls, and how spread out the data is a measure of standard deviation. And then n is your sample size. So how many people were included in your data set. To calculate your confidence interval, you're going to take your critical value, which is usually the mean, and add and subtract your margin of error. And again, the way that we're thinking about this value is that we are confident that 95% of the time, the mean would actually be between this number and this number. So let's look at some examples. Suppose that a random sample of 50 healthy adults resulted in a sample mean body temperature of 98.2. And so just so we know, because we haven't used this notation before, X bar represents mean. And a population standard deviation, so that's sigma, is your standard deviation of 0.65. So what is the margin of error? So 2 is our constant. We multiply that by our standard deviation of 0.65. We divide by the square root of our sample size, which is 50 adults. we calculate that number and we would get a margin of error of 0.1838. Example 2, you want to rent an unfurnished one-bedroom apartment in Boston next year. The mean monthly rent for a simple random sample of 32 apartments advertised in the local newspaper is $1,400. Assume that the standard deviation is known to be $220. Find the margin of error in the pricing. So again, 2 times the standard deviation is 220 divided by the square root of n, which is 32. So there's some extra numbers in there. We want to make sure that we don't use the kind of extra information. So our margin of error is $77.78. So our mean, our average price is actually probably a little bit higher, so about $14.77.78, and a little bit lower, which would be like $13.23 and some change, or $13.22 and some change. Example 3, we have IQ test scores of 31 7th grade girls in a Midwest school district. We've calculated that sample mean is 105.84. and the standard deviation is 14.27 points. Find the margin of error for these scores with 95% confidence. So again, 95% confidence means that we're using the 2 times the standard deviation of 14.27 divided by the square root of our sample of 31 7th grade girls. So our margin of error is 5.13 points. So just those examples are just calculating the margin of error. This last example, we're actually going to find our confidence interval. A particular brand of aircraft averages 620 gallons of fuel per hour during a normal flight. The standard deviation is 34 gallons per hour. So the first thing is to find the margin of error for the fuel used if a sample group of 435 planes were observed. So 2 times our standard deviation of 34 divided by the square root of n for 35. So 3.26. So we have actually a fairly small margin of error, because for our confidence interval, to find the maximum, we would take the mean, which is 620, and add 3.26. So 623.26 gallons would be the maximum. And then to find the minimum, we would subtract 3.26, which would give us 616.74 gallons.